is a professor in the Department of Electrical Engineering at IIT Bombay in the area of speech and audio signal processing. She received her PhD from the University of Florida in 1990. She has been actively involved in the development of technology for Indian music and spoken language learning applications. She co-founded SensiBio Audio Technology. Madam, it is SensiBio or Sensible? You have to,
Sensible.
yeah. A startup incubated by IIT Bombay in 2011 with her PhD and master students. She currently leads an MHRD sponsored Spark project and computational musicology and musical instrument modeling for Indian music. So, with this brief introduction, now I hand over the session or request Dr. Preeti Madam to take over and start the presentation. Madam, please.
Yeah, thank you very much.
Okay.
Yeah, let me just share my screen and then I'll get started. Yeah. Okay, so
Yes,
can someone tell me? You can see my first slide, right?
yes, ma'am.
Okay. Okay, yeah, so welcome all my teacher colleagues to this session. I'd like to start by thanking Professor Patnaik and KIIT Bhubaneswar for this very kind invitation. And as she already mentioned, my area is signal processing. Uh, DSP basically, and I specialize in audio and speech. So signal processing, as you know, is an extremely applied area. So it is a set of mathematical tools, but it's highly applied. And typically, if you want to go do a good job of applications, you have to understand the domain, in which you're working. And that is why, people tend to specialize. So there are people who specialize in biomedical signal processing, some people in image processing and vision, and, some people in audio and so on. So it's, one of those important application areas. And so I'm just going to try to give you a feel of the kind of use that signal processing techniques find in music applications. Okay, and as I said, I cannot see the chat all the time, but please feel free. I also leave some time in between for questions, but feel free to ask questions. I don't have a whole lot of material. More importantly, I just want to give you an idea of some of a little understanding of the field and some of the excitement associated with it. Okay, so what are some really popular music applications that actually incorporate a lot of machine learning, or what is also called artificial intelligence? So I've listed three major categories here: music recommendation. Anybody who uses a music streaming service knows that when you log into the service, it will often have suggestions for you. And the suggestions are kind of based on your listening history, and that's called the music recommendation. Of course, we are used to seeing recommendation in other fields also, right? Because we've seen, even if you are looking for items, let's say on Amazon or some, e-retailing site, there also we receive recommendations in terms of, they try to show you items that they think that you are, likely to want and to buy. So recommendation itself is a very vast area, and a very important one, for commercial businesses. On the other hand, in the case of music, what does recommendation mean? Recommendation means recommending particular songs or recommending particular artists to listeners and fans. Another area where machine learning is used also is in music learning, where there are some aids available, like generating accompaniment, for a single performer automatically, or giving feedback on accuracy of singing. And of course, there is also, other background kinds of processing, which processes the audio in order to put some markers in the audio that could help us to navigate the audio to do some guided listening. And finally, the entertainment industry is full of applications of machine learning, especially now. There are a lot of lot of research and development effort in developing tools which are supposed to be intelligent and can help even creators of music. So there are audio processing tools like big workstations which allow you to, manipulate some of the recorded audio, or to generate some, additional audio that you can combine with it in order to improve the quality or make it more interesting. There is also computer assisted composition. There'll be suggestions by the machine on what, how to incorporate more interesting features into the music that is being created. And of course, ultimately, the artist is the one who takes the call in terms of what to use and what to not use or what to modify. And of course, computer assisted instrumentation. If you have a single track, you can still use technology in order to generate suggestions for the instruments that will go with it. So it's really quite vast, and it's only natural that some of these applications are up and coming and growing to assist listeners, to assist music creators, to assist learners, and so on. Okay, now what is different about music recommendation from other kinds of recommendation? Like I said, the type that you will get, let's say, on Amazon and some other services. Music, what happens is, what is right in terms of a recommendation depends on, many factors. For example, apart from a person's taste or a person's individual culture and, likings, there is also the listening context. Okay, so even all of us who listen to music may not want to have the same preference for the music at all times, right? It also depends on the situation. So even if you look at some playlists which are created by streaming services, they'll have a playlist for the party time and a playlist for, calm and quiet listening. There are playlists generated for people when they are driving or they are commuting to work. So there are many different listening contexts also, in addition to, let's say, a particular user's individual, tastes or their background and culture. The other thing in music is repeat listening is very common, So it is not like when you buy something, you keep buying the same thing. But on the other hand, in the case of music, people do indeed like to listen to the same music again. So all of this makes music recommendation quite unique. And finally, what is really used? What are the underlying principles of music recommendation? So one of the first principles is what is called collaborative filtering, and that is actually common for all kinds of recommendation. In the sense, even for buying general items, like I mentioned from e-commerce sites, they all use collaborative filtering. And the meaning of collaborative filtering is that they analyze the items bought by a range of users. And from that, they create some sort of a matrix or a grid from which they can predict, similarity between users. Okay, so if they find somebody with a past history very similar to yours, and that person, goes and buys something, then there's a strong possibility that since you have a shared history of buying the similar items, that item will be good to recommend to you. So that's called collaborative filtering. Then there is other kinds of information, such as by applying natural language processing to blogs about songs. So people may have written about the music. So from that, they can, get some textual description about the song, and then use that textual description to see, that becomes associated with that song. And then songs with similar descriptions will be clubbed together and they will be recommended more or less together. And finally, there is something called content based, and that is what we are really concerned with, because it involves actually analyzing the audio to find out some musical attributes. So maybe there is a new artist who has put out a new song, in which case we are not expecting that any previous users will have actually, experienced that song. We may not have any blog already written about the song, but certainly we can process the audio recording or the audio, the piece, the music piece, the audio of the music piece, to find some musical attributes, such as the tempo of the song, right? The beats per minute. Is it a fast song? Is it a slow song? Is it a song with a lot of loudness dynamics? What is the mood of the song? Now, that also is kind of related to the musical material that is used in the song. So this is where audio analysis comes into the picture, and actually the focus of my talk today is actually the audio analysis part. And my purpose of telling you this was to give you a kind of a perspective on where one of the applications of uh, essentially finding audio analysis to be important. Okay, so this is an area called music information retrieval. In the sense, we are trying to find out information about the audio or analyze the important attributes or parameters of the music from the audio signal. And it refers to the extraction of semantically meaningful information from the audio waveform. So we essentially have only the waveform because that is what is stored in a digital audio file. And we will carry out some processing on it in order to get some meaningful information. Now, what is meaningful information for music really depends on what do listeners listen for, right? And this area is called content-based MIR. As I said, it's based on analyzing the audio content. Okay, now why do we do this? Because we actually have, as we well know, that digital repositories are very, very huge. And if we can do some content-based analysis and find out some tags for the music, then it would help improve the search and navigation. So some people who are searching for music, actually it becomes easier because they're going to actually tag the audio files by some semantic or some words that make a lot of sense to listeners, and they could in principle use that to search for music. Okay, and the way this is done is by viewing music as an acoustic signal that has certain musical attributes. So we are essentially have very low level signal properties based on the waveform, but we are going to build a bridge between those signal properties and some very high level description of the song. Okay, and I'll talk in a minute about what is that high level description, and that is actually the main goal of audio MIR. Okay, so in this particular tutorial, I will discuss what are these attributes, and I will talk in particular about vocal music, so about singing signal properties. And we will talk about, then we will talk about a series of applications. Okay, now singing itself, although we all understand it's also about using the human voice to produce music. Singing, of course, is a dominant part of many, many cultures. And that's why singing itself has a huge diversity. First of all, we know that cultures have different kinds of music and different kinds of instruments that are used. But on the other hand, the use of the human voice is almost universal. It's considered a very important kind of musical instrument. But obviously, we know across cultures, there's a huge variety. Okay, so I have some videos. I'm not really going to play the videos, but just to show you that there is so much diversity in music. So this is a pop song from a band. From an English band, something that's kind of very popular in the West and also among youngsters across the globe. This is a video from a Carnatic music site. You can see this is a very famous singer, Subbalakshmi. Here is a video from Chinese opera. Okay, so this is yet again a different style of singing altogether. And finally, we also have music from the Middle East, which again has had its own history and evolution, and it's a particular style of singing and with a particular type of instrumentation. Okay, and of course here we have gospel music. That's again comes from a particular culture and is a genre by itself. Okay, so let's talk about, okay, so all of this is basically vocal music. And so when we talk about analyzing music, we have to know that even vocal music comes in so many different forms, and we need to try and identify some properties which are likely to be universal and can be used to describe any of these types of music. Okay, so that's the first part of my talk, and this is where I'm going to get started. Okay, so let's talk about what we mean by decoding music. In the sense, we are trying to analyze music in terms of some more basic components, and what are those basic components. Okay, so now it turns out interesting sounds are typically coded in the form of a sequence of atomic sound events. Okay, so by sequence of atomic sound events, I mean very basic components. So for example, we could look at music as an evolving pattern of notes. Okay, so very simply, we could say that a piece of music is really revealing to us a sequence of notes as they are evolving in time. Similarly, when we talk of speech, as we are speaking, for example, we are saying a lot of words, but we are also the words themselves are comprised of more basic sounds, right? And one of the most basic sounds of speech is what we call phones or phonemes. So an atomic sound event, that is a very basic sound, itself is a complex acoustic signal, and it has a set of what we call temporal and spectral properties. And when that particular sound falls on our ears, it evokes a certain sensation. So we are able to either recognize the sound because of the properties of the sound, right? Or we are able to say that, okay, it reminds us of something, or it is close to some other sound, that we have experienced. So that's what we call the sensation. Okay, so let's take a single musical note. So this is an extremely simple sound. Okay, I'll just play that for you. So the way I've got this player set up is because we could not directly play from the screen. I'm playing through my speaker. So I'll just increase the volume of the speaker so that you can hear. Okay, so I'm going to play this now. Okay, so I hope you heard that.
Yes, ma'am.
Okay, so that was a very pure tone, extremely pure. It was almost sounding like, some, musical instrument with a long sustained sound, maybe like of a horn or a trumpet. And if you look at its properties, okay, so now what I have plotted here is a small segment of the waveform of the sound on the left, okay, and on the right hand side is the magnitude spectrum. Okay, so in signal processing, we are all familiar with looking at a signal either in the time domain or in the frequency domain, both of which essentially have equivalent information because we can go from one to the other via the Fourier transform. But on the other hand, some of the properties of the signal are much more easy to understand in the frequency domain. Okay, so in the time domain, we see that this signal is a very simple periodic signal, right? It's clearly periodic. We can see it's just all the cycles are repeating. In the frequency domain, we see that this particular signal has only discrete frequency components. Okay, so, and there's something very special about the way the components are related to each other in terms of their frequency location. So for example, I have one component at 200 Hertz, the second component at 400 Hertz, the third component at 600 Hertz, right? So what do we say about this relationship between components? Does anybody know what this particular relationship is called, where the components are all a multiple of a fundamental frequency?
Harmonics of a frequency.
Okay, excellent. So these are all harmonics, right? So a periodic sound actually is always associated with harmonics, in the sense a periodic sound, because it has a period, it has something called the fundamental frequency, and that is the lowest frequency component in the sound, and all the other components are related to it by this multiplicity relationship. Okay, now the amplitudes are pretty arbitrary, right? I have shown some amplitudes here. This sound was actually synthesized by combining all these sinusoids. That is a sinusoid of this amplitude at this frequency plus another sinusoid of a slightly lower amplitude at the second harmonic, and so on at the third harmonic, and so on. Now, if I change the amplitudes of the sound, then what is going to happen? My waveform is going to look different, but it will continue to have the same periodicity. Okay, so the fundamental frequency corresponds to the period. The period is what I would measure. I can even measure in the waveform. Okay, so in fact, a lot of sounds in nature are periodic. Of course, there are also very aperiodic sounds, or what we call noisy sounds. So let me give you another example of sound. Most music, in fact, nearly all music, except possibly percussion instruments like drums, produce periodic sounds. Okay, because periodic sounds are associated with a pitch or a note value, right? And a note is a basic component of any music. Okay, so let me talk about what are the sensations that the periodics we associate with a particular sound. So there are any sound we can measure. For example, these what we call as the physical attributes of the sound. So the physical attributes of the sound are the intensity of the sound, right? So that is just we take the amplitude squared, and that tells us the intensity of the sound. The intensity of the sound actually is perceived by us as the loudness. So if I change the intensity of the sound, I can make it louder or softer. Okay. On the other hand, if I change the fundamental frequency of the sound, then I can make it higher pitched or lower pitched. Okay, so the what we perceive as the pitch of the sound, like a high pitched note or a lower pitched note, and of course we have a whole range of pitches, right? They are linked to the physical property that is called the fundamental frequency, and fundamental frequency is related to the period, like we just saw in the previous sound. Then there are a whole lot of other properties of the sound, which we call as the spectrotemporal properties, which, for example, in this sound is like what are the relative amplitudes of all the harmonics, correct? So what is the spectrum shape of the sound, right? How do the amplitudes change as we change the frequency of the sound? Okay, so this is called the spectral properties of the sound. So that's also important. And that gives us a quality called the timbre of the sound, or the quality of a sound. Okay, so for example, if I play the same note with the same loudness on a violin and on a flute, for example, right, then I might get two notes or two sounds which have the same pitch and the same loudness, but they would still differ from each other, because we would be able to recognize that this is a sound note from a flute versus a note from, let's say, a violin, because of the timbre. Okay, and that will be seen in the spectrum because there will be different relationships across the amplitudes of the components. Okay, so these are what we call and there's a word here, temporal, also, because there's another property associated with the timbre, and that is called how the envelope of the sound varies in time. Okay, so consider, for example, an instrument like a guitar. If I pluck a guitar string, then it will have that single note. The energy will rise rapidly. After the pluck is released, it will decay rapidly, but it will also sustain for a while, and then it will finally essentially die out. Okay, so this envelope in time as to how the energy of the sound varies in time is also important to the quality of the sound. Right? From that envelope, we can tell, for example, is it a plucked string instrument or is it a bowed instrument, and so on. And of course, the spectral properties are already mentioned. It's about how the amplitudes are distributed across frequency. Okay? So this is called the timbre. The other word for timbre is the tone quality or the color, and in music it is usually linked to the identity of the instrument that is producing that particular tone. Okay, so this is what I already described. We have a spectral envelope and we have a temporal envelope, and then there are some also other issues. For example, some sounds may be characterized by some amount of irregularity also, and also because of the way they are produced. So for example, if you are playing a violin, there may be some scratchy kind of sound coming because of the bow interacting with the string. If you're playing the flute, for example, there's going to be some breath noise being released with the flute, right? So that's going to give that's also very characteristic of the instrument. So all of these together actually contribute to the quality or the identity of that sound, and that is what we use to recognize the sound or to label the sound. Okay, so are there any questions at this point?
Any questions?
Yeah, please feel free.
Yeah.
Okay, great. Okay, so as I said please feel free to ask, because then I'll know, because there are a lot of things around each of these, and I'm just using my judgment to what to share with you. Okay, so let's talk a little bit more. Like I said, my more of my focus in this talk is going to be on the human voice. So let's talk a bit about that. And like I said, the human voice is one of the most sophisticated, if we categorize musical instruments, is one of the most sophisticated mechanisms, considering, sound producing bodies. And the human voice actually comprises of the source of our voice. What we call the sound source is what we have deep down in our throat. Okay, so we have a pair of vibrating vocal cords which close and open, and because of their opening and closing action, they release puffs of air from the lungs. Okay, so if we are just quietly breathing, then what happens? We keep the vocal folds open and air gets released, and there is no sound produced because it is a free flow of air, right? When we wish to speak or wish to sing, then we start vibrating the vocal folds, and that essentially modulates the airflow by releasing puffs of air. Okay, and the rate of vibration of the vocal folds controls the rate of release of these puffs of air, and in fact that controls the fundamental frequency of the sound we produce. Okay, so the pitch of the sound we produce really depends on the rate at which we vibrate our vocal cords. Now what happens? The vibration of the vocal cords can be viewed as just narrow puffs of air escaping from the vocal folds. Okay, now by itself they are not very energetic, or at least the sound they produce is very, very basic. But what really happens is this sound, which is of the opening and closing of the glottis, passes through the rest of the vocal tract, right? So we have the vocal folds and then we have the vocal tract. The tract itself is made up of the oral cavity, which opens out at the mouth and the lips. As that sound, very basic sound produced by the vibrating vocal cords, travels through the cavity, it undergoes a spectral shaping. Okay, and the spectral shaping comes about because we can view the whole oral cavity, starting with the vocal folds right up to the mouth, as being a tube, a hollow tube. And the hollow tube has certain preferred natural frequencies, which we call the resonances. Okay, so depending on the length of the tube, we have all these different resonances, and the resonances themselves can be changed by changing the shape of the tube, right? So as we change the shape of our mouth, what happens is we change the shape of this tube, and that changes this mechanical system, and it changes therefore the resonances of the mechanical system, and we get different spectral shaping or different kinds of filtering of the sound that is leaving the vocal cords. Okay, so for example, we can get a variety of different sounds by shaping the vocal tract. So for example, if I keep my mouth wide open, I can produce a sound ah, because my vocal tract has a certain wide open shape, right? On the other hand, if I make a narrower opening in the front of the mouth, we can produce a sound e. Okay, and how are these sounds different from each other? Because the resonances of the tube are different, because the shape of the mouth is different. We can produce completely distinct sounds which we perceive as A and E. On the other hand, if you keep the shape of the mouth the same, but you change the vocal fold vibration, then what aspect of the sound do we change? We are changing the fundamental frequency, right? And that is what you can see on the left-hand side, where I have two different spectra, one with the high fundamental frequency and one with low fundamental frequency, but both of them have very similar resonances. Okay, so the sound that we hear, it has a spectral shaping that is based on vocal tract shape, which controls the timbre of the sound, like we said, but it also has a pitch, and the pitch is controlled by the vocal fold vibration. Okay, so what is the difference between speaking and singing, right? In both cases, we are going to use the vocal apparatus. When we speak, we produce many different words. So we speak the different sounds such as a, e, p, t, k, and so on. In each case, we are changing the shape of our mouth to produce the sound we want. So we change the shape of the mouth not only by moving our lips and jaws, but also moving the tongue to different locations. So if you think about when you are speaking, you're actually moving your tongue a lot, because the tongue is actually influences this vocal tract or this cavity, and it is actually changing the acoustics of the signal that is passing from the vocal folds to the lips. Okay, so from the properties point of view, we can also sing words, and music has evolved, and it is a very special kind of a human sound production. Uh, so if we consider it, of course, we know in theory that this is the case, but practically speaking, it is very nice to measure and find out. So I'll just play to you from a certain data set, which has a particular speaker speaking a sentence and then singing the same sentence. Okay, so it is taken from the lyrics of a song, but they had the singer not only sing the lyrics, but they also had them actually speaking it as though they were speaking normal speech. Okay, so what I do is I'll just go ahead and play the sentence to you, and I'll also play the the singing version, and then I'll tell you what is this property that we are commenting on.
There's a calm surrender to the right.
Okay, let me just make my audio a bit louder here. Okay, and now I'll just go back to my full screen. Okay, maybe I'll play the singing first, and then I think that will make more sense. I'll play the actual, as the singer, as she's singing a line of the lyrics.
There's a calm surrender to the rush of day when the heat can be turned away.
Now the speaking.
There's a calm surrender to the rush of day when the heat of the rolling world can be turned away.
Okay, so it was the same speaker. She first sang and then she spoke the same sentence. Now, if we were to analyze the pitches, right? Now, in the singing, you heard that she sang a lot of different notes, right? So, if we were to process that waveform that we get in singing and extract the pitch at a very closely spaced instance of time, and if we do the same for the speech, we get this plot, which is actually the distribution of the pitches, a histogram distribution. Okay, and this is shown here on a logarithmic frequency scale. So what we find is in singing, the pitches tend to fall on a grid. So we typically have the pitches concentrated in certain regions and not so not so present in certain other frequency regions. But in speaking, we have a distribution of pitches which more or less is continuous throughout the range. Okay, so now this is something we know because we know the importance of singing very tunefully, that is singing the correct notes of a song, and the notes themselves tend to be defined as a set of discrete pitches, right? The same thing holds in terms of timing. Okay, so if we look at the timing of the different syllables in the singing and in the speech, what we see in the speech, there's no particular pattern, right? We have a range of timing. But on the other hand, in the singing, the timing tends to again fall on a grid because we use something like an underlying beat, right? When we sing, we are singing in time to some underlying beat. And that is also what shows up in when you look at the distribution of the durations of the syllables. So these are some properties that contrast, speech with singing more generally because it is speech which is set to some kind of a musical framework that constitutes singing. Okay, so now this can be actually seen very clearly if we look at what we mean by this changing pitch. So I'll just play this for you, which is a very short melody, and then you can see over here which is something like the notes of the song as they evolve in time. So when you're listening to the melody, you can just follow along and see these notes. Okay, so these are all discrete notes, and they're sounding very musical because they are drawn from this set of so-called allowed pitches in music, and that is true for all music actually. It tends to use discrete pitches, and we can also see the vertical lines, right? What do the vertical lines refer to? This is a timing, correct? So there are some short notes and some long notes, but the long notes are a multiple of the duration of the short notes, right? So the music follows a very strict time grid and also a grid of discrete frequencies, right? And all the notes here are essentially the notes of the scale. Okay, so now this musical scale itself, we can understand a little better by placing the notes out like this. And we begin to see that, yeah. Was there a question?
No question. What the hell is this? Got stuck out? No. Oh, you.
Yeah, I couldn't hear that. Was there a question?
సుభద్ర ఏ ఆమె పెళ్లి కుదిరిందా నో ఎవరైనా
Madam, just mute yourself.
I think someone muted by mistake.
I can't mute anyone. I think your host has to do that.
I think Sujita ma'am. Sujita ma'am has muted, I guess.
Madam Suchita, please mute your mic.
I think the host can do the muting. No, Sujita probably can't hear.
Mom, what is this, mom?
Okay, so I think Sujita madam got that message. So maybe we can continue then. Yeah, so any questions at this point?
No, madam.
Ma'am, this periods depends upon the sampling algorithms.
Which what depends?
Sampling algorithms, ma'am. We do samples, no? We do convert analog to digital, right?
Correct, correct.
Does these periods vary depending upon the sampling algorithm? For example, Nyquist sampling.
Okay. No. That does not. Actually, the pitch depends on the absolute period, right? So what I showed you in one of the earlier slides as the period of the sound.
Yeah.
Okay. So this is in time. As you notice, we have written here time in milliseconds, right?
Hmm.
So irrespective of the sampling, it has to be sampled at the Nyquist rate, right? Otherwise, you won't preserve the properties of the signal. As long as you choose any sampling rate that is above the specified or above the Nyquist frequency, you will essentially hear the same pitch, correct? Because the pitch actually depends on the analog properties, which is the pitch period in seconds.
Okay.
Okay, so when you convert a sound to digital, in fact, we cannot, as long as it is sampled at the correct rate, as far as we are concerned, it sounds exactly like the analog signal, because when it is played out, it is reconstructed, correct? We cannot directly hear a digital signal. We have to play it out by converting again from D to A, right? And then only we hear it, right? So as long as the sampling is correct and it is known to both the A to D and D to A and it matches, we'll get back exactly the same time domain signal in terms of the continuous time signal.
Okay,
right?
ma'am.
So human ear can only hear the continuous signal, continuous time signal. Digital signal is only for the purpose of storing and intermediate processing and so on.
Okay. Thank you, ma'am. Right.
Yeah, you're welcome. Yeah, thanks for the question. Yeah. Okay.
Ma'am,
so,
is there any instrument to measure the vibration of the vocal fold?
Directly, yes. There is something called a glottograph. Okay, so that is used to, you place it on the throat and it measures the vibrations directly by passing a current. It measures essentially the tissue conductance because the vocal folds, they close and open. So the air gap changes and then, basically the current changes. So yes, there is a way to measure it directly. But of course, we can also analyze the signal itself. right? Because when we look at the speech signal, we will see its periodicity, and there are many signal processing methods available to measure the periodicity of the signal.
But when we measure in the glottograph, is there any interference of the vocal tract also there?
Because it is measured directly from the throat, you know, the glottograph is actually placed on the throat. It is quite free from any vocal tract influence. Okay, it directly measures the opening and closing of the vocal folds.
Okay.
Okay. But if you measure the speech signal at the lips, like the way we do, you know, we place a microphone just outside the mouth, then that is giving you the combined effect of the folds as well as the vocal tract.
Yes, yes.
Okay.
Okay, thank you.
Yeah, sure. Okay, so yeah, so we were talking about this. So there are certain fixed, you know, pitches that are used in music, and that actually turns out this is very interesting because it's somewhat universal across cultures. These particular sets of pitches, you know, across cultures across the world, from ancient times, it has been found that all you know cultures have used discrete pitches, and they usually have the similar relation to each other. The different you know fundamental frequencies that are used to make up a musical scale. And there is a very special relationship called octave, where there's a doubling of frequencies. And the really interesting thing is that they are spaced out in a logarithmic manner. Okay, because our whole human hearing is actually follows a logarithmic scale. So the distance between the notes, it is not an absolute value in hertz, but rather it's a ratio. Okay, so this octave is a doubling of frequency. But if we go, for example, to an adjacent note, then there are altogether 12 such intervals from one across one octave, if you measure all the white keys and all the black keys. So it turns out that the ratio is 12th root of 2, going from one note to its adjacent note. Okay. Of course, there are small variations. For example, in Indian music, we have something called a slightly different scale, just intonation, where you know, the ratio is a little more finely tuned. It's not just a 12th root of 2, but it is the nearest integer ratio, small integer ratio to that. But the point I'm trying to make over here is that yes, there's a relationship. It's roughly logarithmic, and there are, you know, discrete pitches that can be described in this manner. Okay. Okay, so now we come back. So that was some very, very basics of saying that, okay, at the very low level, the attributes of music can be viewed in terms of the description of the notes, and a note itself can be described by its fundamental frequency, the shaping of the amplitudes in the spectrum, and its intensity, and so on. Okay, but of course, music is a much larger, you know, sort of an entity that we sort of listen to and understand and react to. So the point is that how do we understand the more high-level attributes of music? Okay. Now, the audio processing that we do for the characteristics of music really should be based on how we perceive and understand music. Right? Perception and cognition, because all the applications have to be made to serve the listener or to serve a musician, correct? So we need to understand that what are these so-called higher level characteristics of music that a listener are important to a listener, or the listener uses to make sense of the music. Okay, and then of course we need to understand the end applications that we might want to use it for. Okay, so now to just give you an easy to understand example, maybe something that's a little, you know, music is also not that difficult to understand, but it tends to be a bit abstract. So if you want to write an application for image retrieval, so we have a query image, okay, which looks like this, and I have a database of images, right? Now it's very easy for us as human beings to immediately spot the correct image in the database, right? This shows a tiger, and therefore the correct match is this one, the one with the tiger here, right? But for an algorithm to do this, you can imagine how difficult it is, right? Because the way we figured this out so quickly is by understanding the image. We understood that this image, we interpreted the image, which is actually the image is nothing but a bunch of pixels. of different, colors and intensities, and we interpreted that to show us an animal which we recognized as the tiger because of the, particular shape and the particular color and the patterns on its skin. And we saw that the tiger is moving across some kind of, landscape over here. And then we made, having understood that, it's kind of finding out the meaning of the image, we were able to identify another image which has the same meaning. Okay, so although the color schemes are quite different, this second image in the database actually has a lot of background which is completely different from the query image. Also here the tiger is lying on the grass and here the tiger is walking. So there are a lot of differences at the signal level, right? At the image signal level. But we are able to do it because we are able to actually understand, interpret, and then find out, how these images are connected to each other. So what does that mean for music? Okay, so that's what I meant. We use image semantics. That means we interpret the meaning. Okay, now the semantic there's another simple explanation for that, and that is called similarity, right? So what was this query thing about? That I had a query, I wanted to find something similar from the database, right? So my explanation was of this application is that similarity is important for me. So I have given you an example and I want some images similar to the example that I have produced, right? So if I ask you, okay, take this blue ellipse here, and I ask you that from all the remaining images, find out the one that is most similar, right? So can you give us, is there a unique answer to this question?
No, ma'am.
Okay, why not?
Because there are two objects with this unique feature.
Okay, and what are those?
A pair of two objects.
Okay, so there are two kinds of similarity here. So if I do find the one, then you will ask me what kind of similarity, right? There is one color similarity, in which case, the two blue objects can be considered to be same. And then there's another shape similarity, right? In which case this ellipses can be considered to be similar. Right? So when we talk about similarity, we must understand that there are many dimensions, and what the dimensions are also depends on the domain. Okay, so in the case of the image, color, shape, and all of these are important, right? So what shall we say for music then, right? So let's first consider the slightly easier problem for us, that is about speech. So what do we mean similarity in speech? We would say, okay, if two people are speaking the same sentence, we might say that, okay, these two sentences are similar, they're being spoken by two different speakers. In which case we would say the underlying sounds which make up like the words and the phones, they are same. We could also say that two people have the same accent, or they are speaking the same language. So they're not saying the exact same words, but they're speaking the same language because although all those words have something in common, they are drawn from the same language. Similarly, we could say that this is two different sentences, but it's spoken by the same speaker. And in that case, what is the similarity? The voice or the manner of speaking is the same. So I can identify the speaker. Even if the speaker says something else, I'm saying that I can identify them because there's a big similarity in terms of the speaker characteristics, right? So there is something called perceived similarity, and there are many particular dimensions of similarity, right? We cannot just, say very generally speaking that two things are similar without qualifying what particular aspect of similarity or notion of similarity we are using. Okay, fine. So now let's look at similarity for music signals. So I'm just going to play some pairs of signals, which according to me are similar to each other in some sense, and what I want you to tell me is in what sense are they similar. Okay, fine. So maybe I'll just make sure that the volume is okay. Okay, so please listen closely. I'll play a pair and then we'll comment on how they're similar and we'll move to the next pair. Okay? And what I'm trying to illustrate over here is there are many underlying notions of similarity that we can use for music. Second. नया Okay, so would we call them similar?
No.
Yeah, in terms of words, it's similar.
Okay.
Language also similar.
Okay. But are they different? Could you tell the difference?
Yeah, pitch probably. I think the pitch is different.
Anybody else?
And the loudness also.
I beg your pardon?
Yes, loudness is increased in the second one.
Correct. Okay. And was there anything else? Was it just a matter of loudness only that I just turn up the intensity, or was there something else?
It was bass effect in the second.
It was what?
Bass effect.
Bass effect. Speaker bass effect.
Bass. You're absolutely right. Okay, so that was a good observation. See, what we had done is the second one was the so-called original audio. The first one was playing out that original audio through a telephone. Okay, that is transmitting it in a voice channel. Now, voice channel, as we know, has a 300 hertz lower limit and 4000 hertz upper limit. So both the very low frequencies, the bass frequencies, and the high frequencies were cut out. Okay, so that was a change in quality. So it's exactly the same piece of music, but one was transmitted through the phone channel and the second one was actually the original. Okay, so we can see that actually there's a lot of spectral change that has taken place, right? But on the other hand, we still recognize it to be the same song. So some of the musical attribute, nobody will deny that they are the same song, correct? So, you know, the musical attributes have remained the same, but the quality has changed, and that change is more of a band limiting kind of change. Okay?
Okay.
Fine. So now I'll play the second pair, and again you have to tell me what is the difference. What is the similarity and what is the difference? Of course, according to me, they are similar, but we have to determine in what sense they are similar. Okay, next one. Okay, we agree it's the same song?
Yes, ma'am.
Okay, so what was the difference, if any?
Maybe, ma'am, the sampling rate is different. It has been sampled at a lower rate, and this has been sampled at a higher rate. So in between samples have been skipped, and it is being played faster that way. Maybe.
Okay.
I mean.
Okay. So the point that anybody else?
Different. Somewhere the sticks are there, somewhere the bass drums are there. Both the musics.
Okay, 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 good. Anybody else? Okay, so I think there were two observations that came out. One is about the speed, correct? The second one was faster. It was at a faster tempo, right? And the second observation, which is also, it's about the instrumentation has changed. Okay, so this is actually what this song is, what is called a cover song. So the original song has been recreated by a different band with different instrumentation, and they've changed some of the attributes, most notably the tempo. Okay, so in terms of the listener perspective, the listener will say this is a faster version of that. So it's actually a completely new production. It has been played faster, and they've also used different instrumentation. Okay, fine. Okay, so now I'll play another final pair, and now again you have to tell me whether you consider them similar, and similar in what sense. Okay, second one. Okay, how about that one?
In this, ma'am, I guess the music is same, but the singers and the language are different.
Okay, anybody else? How is the music the same?
I think different musical instruments are used. Both,
Yeah,
No,
but
in the
what is
same
it?
music is the same type, but language is different.
Okay, so it is a tune which is the same, right?
Yes, yes.
Okay, so it's not, when you say music, it's a very broad term. What we are saying is the melody or the tune is the same, right? So what has happened is this original song is an original song by a German band called Bonnie M, and this one is from a Tamil movie. Okay, so this is what one might call a tune piracy, right? So you just lift the tune and then you generate another song, and the other song is completely different. Obviously, it's a different language, different singer, different words, different setting, different instrumentation, and all that. But there's something remarkably similar about at least one important attribute, and that is the melody, right? Any comments?
Yes, yes, madam. Yes.
Yeah, so that is what we call. In fact, this was one of those applications where somebody might accuse someone of some infringing a copyright, right? So, but it's very, very difficult to judge that from just the audio signal. You require such a high level. Human beings can listen and say yes, it is sounding similar in that sense, but it's actually different in so many other senses, right? Okay, so that's the point. And like I said over here, this was the same music. This is a cover version that is recreating the same song, right, by a band, different band. And this one is the same tune. And we can go on like that if we relax. So this we can say is a relaxation of the similarity, right? This is strictly the same. It was exactly the same song. This is a reproduced song. This is actually a completely different song, but the tune is the same. So some very, very core attribute is shared, right? And we can go on like that. We could have different music in different scales or ragas. They would actually be quite different, but they would still share something. They would have the same set of notes that they draw from, correct? And then we could have something called the same genre. That is, let us say it is drawn from the same culture, like all Bollywood music. It's all the same genre. Or all Hindustani classical music is the same genre, and so on. And then finally, we could have songs which are cutting across cultures but have the same emotional value. For example, all generally fast tempo music sounds very happy and energetic, and slow tempo sounds more calm, and so on. Okay. Okay, so now the point is that if you have to do signal processing to uncover this thing similarity, then the question is that, okay, so what is common, right? When I look at a waveform, it's extremely difficult. It's a typical waveform, right? If you look at your audio signal in a waveform editor, there are many waveform editors. That means you can open an audio file and you can actually see the waveform, you can play the waveform, and so on. Okay. Then if you do that, you will see something like this. And from this, it's really difficult to tell. Two waveforms will look completely different. And it's very hard to say it's the same song or what is shared between those two pieces of music. Correct? It's not the waveform. Waveforms are never similar. Frequency spectra are also very complicated and very dissimilar looking. So it's not possible to do that. Temporal variations also we cannot make out very clearly. What we can try to match is the musical dimension. So for example, we could clearly say in one case, the tempo was faster, slower. Tempo belongs to the category called as rhythm. We can say the melody was the same or different, right? Timbre is the instrumentation. So when we talk about similarity and difference, we cannot really relate it so easily to the waveform properties or the spectrum properties, but we can definitely talk in terms of these musical dimensions, which are the melody, rhythm, timbre, and so on. Okay, so this is what we had, that the higher level musical dimensions had to be compared. So in one case, we were able to compare the melody, we are able to compare the tempo, we are able to compare the timbre, which is the instrumentation, the lyrics, the mood, and so on. So when we talk about music similarity, although we understand the signal properties, we still need to understand how the signal properties tie in with these musical dimensions. Only then are we going to be able to comment on musical similarity. Okay. So we need these concepts, music concepts, called melody, rhythm, and timbre mainly. The melody is based on the pitch of the notes, right? So we talked about the tune of the song, and what is the tune of a song? A tune of a song is essentially the sequence of note pitches. We can also talk about the rhythm, which is based on the timing information. So that is related to fast and slow, and it's also related to something about the strong beats and the weak beats in the song. Okay, and the timbre is a property which relates to the overall instrumentation. Okay, so if we want to do anything in music recommendation based on analyzing an audio signal, we really need to first find a way to get to these high level musical dimensions, or some way bring these into the picture. Otherwise, it's not possible to rate the similarity of songs. So representation of these high level attributes can be obtained from the pitch and timing information extracted by audio signal analysis. Okay, so once we get to that level of the high level attributes of music, then we can compare, correct, whether two songs are similar. How similar is the tune, for example? How similar is the melody? How similar is the rhythm? Or how similar is the tempo? Okay, now in order to compare these attributes or to extract these high level attributes, we need to understand something about audio signal representations. Okay, so as I said, is in machine learning, the input signals that we give for machine learning really have to be represented in a particular manner, and they have to be represented in a manner that all the properties, important properties, are evident. Okay, so it turns out that for audio we have to use a very special representation. We already saw some spectra, correct? So spectra is essentially the Fourier transform of a signal, and then if you take a magnitude, you get a magnitude spectrum. Now, if I just take the spectrum of a signal, like you can see over here, I have a waveform. I took a spectrum. I saw there are 3 peaks. So I can conclude there are 3 frequency components in the signal. Correct? But in general, audio or music, it does not comprise of just a set number, a set type of signal for all the time. The signals actually change, right? We hear different notes. And that's why music is interesting, right? It's not all about playing just one continuous note. It's about changing notes, which gives rise to, let's say the melody of the song. So there's a lot of change happening in the signal with time. And that is what makes the music actually interesting, an interesting signal. So this second waveform is more like what we call a music signal because it has a changing notes, right? So we have one sinusoid, and after some time we have a different higher frequency sinusoid, and after some time we have an even higher frequency sinusoid. Okay. Now, if I just took the magnitude spectrum of this waveform, again I would get 3 peaks because there would be 1 peak contributed by each of these segments. Correct? But this tells me nothing about the tune of the song. Why? Because now I'm seeing 3 peaks. I don't even know in what order they came. I can't even make out that they came one after the other. Right? So this is not a suitable representation for audio signals. What we need is something more sophisticated, which is called the short time Fourier transform. So what is the short time Fourier transform? It is about splitting the signal into small intervals and taking a Fourier transform of each of the small intervals. Okay, so this can be done by taking a short window and applying it to different parts of the overall waveform. And for each part, we extract one DFT, or one discrete Fourier transform slice. And this is how we see it. So what do we see here in this figure? We see that, okay, this sinusoid was dominating at this time for this window. When I moved the window, it changed to this sinusoid. When I moved the window again, it changed some more. And finally, on the last window, I got a much higher frequency sinusoid. Correct? Our frequency is written here on the y-axis. And I can see that the frequency is continuously increasing, just as I expect from this waveform. Now, how do we depict this? So we have already decided that this is a better representation, what is called not just Fourier transform, but the short time Fourier transform. That is, I need to take a series of Fourier transforms, right? Each corresponding to a short window, right? Okay, so then how shall I represent? It looks very complicated to represent, but there is one simple 2-dimensional view that I can do. And the 2-dimensional view is what is called a spectrogram. Right? So the spectrogram actually shows us all the frequency components as they change in time. So at each instant of time, I have a frequency component. After some time, at some other time, I have some other frequency concentration. At a future time, I have even a different frequency concentration. Okay. So I show this in a 2-dimensional plot by showing time on the x-axis, frequency on the y-axis, and using this color scale to show where the components are lying. Okay. So now from this plot, I can make out there are 3 notes in this song, if this was a song, right? One note was at this frequency, after that came a higher frequency note, and after that came a even higher frequency note. Okay. Okay, so this short-time Fourier transform is a very powerful representation, but we need to understand how to compute it, correct? We need to know, for example, what kind of window to use. If I use a very short window, I will be able to track the frequency very closely, but I will get what is called very low frequency resolution. Okay, so my frequencies will be very dispersed. My frequency content will not be so neatly focused. So there are some things that we need to understand about how to do the analysis. But I think for this talk, it's enough to understand that yes, we can actually get a very good representation of the signal, such as the one that is shown over here, by doing what is called the short-time Fourier transform and using this three-dimensional representation. So it has two dimensions in terms of time and frequency. The third dimension is the color scale. Okay, so it's like an image. We have turned our one-dimensional waveform into an image simply because it actually is a more realistic representation or easy to understand representation of the musical properties, like which note came when. Okay. Okay, so I just show you some short-time Fourier transform. It's also called a spectrogram, right? When we show the magnitude of short-time spectrum Fourier transform, we call it a spectrogram. So I just show you, this is a spectrogram. You can see the spectrogram and you can listen to the music. This is a waveform. So this is showing a guitar clip. Okay, so guitar is playing different notes. So what do we see in the spectrogram? You will see that this is the frequency scale, correct? So the harmonics are very closely spaced. I mean, the pitch is very low. Then the pitch goes up, and finally the pitch goes up quite a lot. Okay, so let's just listen to this clip. Okay, I just try to increase the volume a bit. Okay, so there were several notes of the guitar just increasing in pitch. Okay. The second one happens to be a singing voice, and you can just pay attention to how the singer is actually varying their pitch, right? Almost continuously, because he's singing in a very, very, what shall I say, ornamented style. And because of that, we can see all these harmonics. Okay, so the horizontal lines are the harmonics of the periodic sound. We can see all these harmonics actually moving. Okay, so listen to this. So was that clear? You could hear his voice quivering, right? And therefore we can see all these harmonics moving. Okay. So any questions at this point? Okay, so there are other kinds of considerations in making the representation for machine learning applications, and that another one involves bringing in the logarithmic frequency scale. Like I mentioned earlier, human hearing is logarithmic, so there is something about a mapping between the normal frequency scale in hertz and the scale that we perceive in terms of how we can tell different frequencies apart, called the Mel scale. Okay, so if we apply the Mel scale, then it's all about combining, bands of frequencies in a logarithmic kind of spacing, and we get a slightly different looking spectrogram. So this was the original spectrogram I had of the guitar and if guitar notes. But if I use a Mel scale, I get a slightly different looking picture where I see that there is the lower part of the scale is hugely expanded. Correct. So these are just hundreds of hertz, which is spreading over this. But later I have thousands of hertz packed into the same region. Okay. So it is a non-uniform spacing out of these components. If I look at the components as originally being equispaced in the hertz scale, now they become non-uniformly spaced. And this is indeed what you will come across if you look at representations of sound that are used in machine learning applications. Okay, so now we will look at just the melody representation, which is the temporal sequence of notes. I won't get into too many details here. I prefer to just go into the applications. All I want to tell you is that it is possible to take this kind of spectrogram representation and extract the pitch of the notes and get the melody of the song in the process. Okay, melody detection is essentially a non-trivial problem, especially if the melody is found in the presence of a lot of instrumentation. So if there is a singing voice, but there's also a lot of instrumentation, then finding that singing voice properties by doing the signal processing itself is quite a challenging task. Okay, so you can see a waveform over here, and you can see the harmonics of the voice in the spectrogram. So this is the spectrogram. But you can also see a lot of activity here, right? Because this is all the other instrumentation. So I just play this and you will see it's not only the singing voice, but there's a lot of other instruments, and that is giving rise to a very complicated spectrogram. This is a message from the man on the moon. Correct. So now we saw that there are a lot of drums being played. There is another melodic instrument going on and so on. And what we really want to extract from this is the fundamental frequency, which we would have to find by first using some signal processing to identify the vocal regions. And then from the vocal regions, find the harmonics. From the harmonics, find out what the fundamental frequency is. So if we did all that, we would find that this gives us only the fundamental frequency. So I can play out this and you will know that this is only the tune of the song. So we have successfully extracted the fundamental frequency. As we can hear it, this particular sound is just a very simple sound, but it is capturing the melody or the tune. Okay, so we can do this for multiple voices. Now, what is the rhythm? The rhythm is actually refers to the timing. This is what we find by finding the beginning and ending, right? Mainly the beginning of the different notes. And for example, by seeing how many of the notes are occurring in a unit time, for example, we can know the tempo of the song. Okay, we can even find rhythmic patterns like where the notes are, you know, the beats are, the strong beats are, and the weak beats are. And this is also a description, important musical description of a piece of audio, music audio. Okay, so I won't get into the details of the algorithms, as I said, but we will talk more about a little bit in the time that is left. We'll just discuss some applications. Okay. So one application which is, directly we are going to use a spectrogram is about detecting the singing voice given a piece of audio. So I want to find out where a singing voice is, and then I want to process those parts because maybe I want to extract the lyrics of the song, maybe I want to extract the tune of the song and so on, right? And there are of course multiple other applications, and I'll touch upon one or two more. Okay, so now the way we do all this processing is exactly what I already discussed before. We need to do the short time analysis. That is, I need to take the audio signal and I need to place small windows next to each other. For each window, I need to find the features via the Fourier transform or the short time Fourier transform. And then, of course, we can use that as a representation and do similarity matching using that representation. Okay. So for singing voice, for example, I'll just go to this work where we try to find the singing voice in a number of different genres of music. So we had some Western music data set, Greek data set, Bollywood data set, and so on. And we saw that the voice itself has very different characteristics in the different cultures. The instrumentation is also different. So discriminating from between regions which have vocal content and which have only instrumental content actually can be quite challenging because it's all very different in the different genres of music. Okay. Okay. So there are different properties in different cultures, but I'll just show you the results using a spectrogram. So here we have two pieces of music, and the task was to determine the singing voice and region in each of them. And what we see over here is just the point that I was trying to make as to how the characteristics of the signal as shown in the spectrogram can be actually very different for different genres of music. Okay, so here you can hear on top is a North Indian classical music. Please look at the spectrogram. You can see here in the spectrogram, we can see the harmonic, but they are very much fluctuating here. And then suddenly they become very flat. Okay, so when you listen, you will know where the fluctuating harmonics came from, what that corresponds to, and what the flat harmonics came from. Okay, so just listen to this. Okay, so if you listen carefully, you would have seen the harmonium came in the end, right? And harmonium has very flat harmonics where the pitches just change from one pitch to another pitch, correct? But the voice produces very rich pitch melodic contours because of all the ornamentation. Okay. Now listen to the second song. Again, we have only instrument in one part and only voice in the other. Okay, so here it was the other way around, right? The Shehnai was the one which had all these fundamental the pitch modulations, right? Whereas the human voice was singing lyrics, right? Earlier it was all akar, and that's why there were lots of frequency modulations. Here the singing voice is actually singing some lyrics. So we have different patterns corresponding to the different words or different syllables which are being sung. Okay. Okay, so essentially the problem of finding the singing voice would have to take all of these things into consideration, right? The different properties and take multiple properties into account before being able to determine, okay, that this is the vocal section, this is the instrumental section, and so on. Okay, so we'll go to some other applications of melodic similarity. Okay, this is a little complicated application. So let me get to a little simpler application. Okay, so these are what we call as style variations. So I'll just play this for you. And you have to identify, actually this turned out to be one is a Hindustani clip and one is a Carnatic clip. Okay. Okay, so let me not even play it out. Can you just look at this? Do you understand this? This is showing the pitch of the singing versus time. So can anybody guess which is the Hindustani genre music and which is the Carnatic genre? Okay, so I'll let you listen to this. Okay, now listen to this. Okay, so any guesses which one is from, so what I have shown is only the melody, only the tune. We have removed the lyrics, we have removed the instrumentation and everything. Huh? Any guesses?
Probably the
Second one
upper
is
one is Karnataki.
Which one?
The upper one is probably the Karnataki one.
Okay, any other guesses? Okay, so let me play the original and let's see if you can tell from that. Okay, now let me play the other one. Okay, so actually, Carnatic is known for a lot of pitch modulations. Okay, so this in fact was the Carnatic song, right? And so this problem of trying to find out what is the genre of the music from these two musics really exploited the fact that there are a lot more pitch modulations, that is detecting the pitch and then finding the properties of the changing pitch in terms of the rapidness of the modulation, which helps us to discriminate these two. Okay, any questions? Okay, finally, I'll just take one more application, and that is about assessing vocal performance. Okay, so that is giving feedback to a learner, right? So I'll just go straight to the example. So these are three examples. One is an original song, and one is sung by a trained singer, and one is sung by an amateur singer. Okay, and if you listen to these, basically what we want to do is to be able to give feedback in terms of which singer is more proficient. Okay, and in what sense. So this is the original singer. Okay, now you can listen to the amateur singer singing the song. Okay, and another singer, different singer. Okay, so you would have noticed that there are differences we can easily tell. And this is not something you would see in the waveform, but if you were to actually process this and extract the fundamental frequency versus time, then you would begin to see that the trained singer is much more similar to the original. Although the amateur singer is quite accurate and a really good singer, she's not trained enough to produce all these very detailed pitch modulations. Okay, so this is another kind of processing, that we could actually do. One is annotation. Okay, so and very similar to that, there are certain specific ornaments which singers can learn to do and get feedback on by looking at the pitch. Okay, fine. So what I will do here is I stop at this point because otherwise it's a discussion of the algorithm that is used to discriminate this, which will take us much longer to do and develop further. But I think I've given you a decent glimpse. So let me just get to my final slides, which kind of summarizes some of this, part. So what did we achieve? We have understood or looked at the acoustic aspects of, try to understand the relation between the acoustic aspects and, the high level music aspects in order to see how, what underlies the signal processing algorithms that can be used in these machine learning applications. We saw that a simple spectrum won't do. We need what we call a time frequency representative. Why do we call it time and frequency? Because it had two axes, time axis and frequency axis, and we showed it in a kind of a three-dimensional representation like an image, the short time Fourier transform or the spectrogram. And that was very important as a representation in the similarity modeling. So finding out how two pieces of music are similar, it's important to go via that representation rather than directly the waveform. Overall, human listeners are superior to machines in nearly all tasks. Of identifying, let's say, similarity in music or identifying high-level attributes, and that's why there is more and more research on modeling human perception and somehow bringing human perception into this machine processing. So this can be called as perceptual AI. That is, what is happening now. There is more of a push towards using a lot of data to, develop these applications. So you actually learn from data. The disadvantage of that is you need a huge amount of data. Very often the data has to be labeled So if you are doing a particular task, you need to have a lot of examples of each of the categories in that task. But on the other hand, if you do have a large amount of data, it actually works very well. You can actually discover the underlying representation, underlying features, and also the similarity metrics simply by so-called training of the neural network architecture on the data. Okay, and to deal with shortage of data, also there are a lot of new methodologies coming up called unsupervised learning. Okay, so the field is rapidly advancing. Applications are many. People are very interested in the application. There's commercial interest also, and it's moving a lot more towards using data to solve the applications via neural network architectures. Okay, fine. So I think this seemed to me sufficient, to give you an idea about the field, some of the basics, and some of the applications. So I'll be happy to answer any questions.
Ma'am, which are shown in the last PPT, are they the future research areas?
Actually, they are not. So they are comments on where it is heading. Okay, so the area itself is perceptual AI, that's what we might call bringing perception into artificial intelligence, human perception. Okay, so so these are the basically the different points around bringing more perception into this thing. So why are we doing it? Because we are seeing that performances are not improving very rapidly. So we need to incorporate more perception, and what people have identified is that using these features the way we are doing it by very carefully understanding the properties of that particular signal has a certain upper limit. And if you have more data, in fact, you can remove some of those upper limits, by having architectures that actually learn all their parameters directly from data. And the complication of music is that things happen at many time scales. At small time scales, you have notes which are changing. At larger time scales, you have larger events. For example, music is also known for repetition. If you hear a song, you will hear the chorus, you'll hear the chorus again, and again you'll hear the chorus, right? And that's what's makes music very good for us, because we follow the structure, we relate to the song, and so on. So there are many such aspects, and that's what makes music particularly complicated to deal with. But this is just identifying all those aspects.
Thank you, ma'am. Ma'am,
Yeah.
could you also highlight some recent research areas, if at all we have to pursue our PhD in this area of music processing? What could we probably search for, and what are the research areas that we could dwell into?
Correct. So whenever you're doing any research, it's very good to have an application in mind, especially in such applied areas. So, take an end application, and then essentially, pick some subtasks from that application. Okay, so when we are looking, for example, at the music recommendation, we may want to automatically tag music, right? So maybe like I gave you that Hindustani Carnatic. Maybe we want to recognize the genre of music, from which geography it came from or which culture it came from. Correct? So that's already a big research task. It will involve setting up a data set of different genres of music, or maybe you want to take up a particular, like Bollywood songs, old songs versus new songs. Can we automatically classify them by analyzing the audio? Because all the tags that we might generate would help us to sort and to annotate or label a database so that it can be more easily used in music recommendation. Correct? So if you understand these kind of, understand how to define an application, and then you go back and see, okay, how are you going to actually go about that application? What is the algorithm that you're going to use? What is the signal processing you're going to use? What is the machine learning you're going to use? Then you will find, okay, that comes under the general category of genre recognition, and you can go and read the research papers in that area, right? And implement something, try it out on your data set. Chances are that your data set is quite unique because you are using some different kinds of music, and you may have to come up with some new contributions in terms of changing the machine learning setup in order to do slightly different architectures, maybe use different kinds of feature representations, and so that would constitute the research.
Okay, thank you, ma'am.
Ma'am, what is the effect of acoustic environment where we are doing the recordings of the music signal, and how you go on modeling the human perception of that music? Is there any effect of the acoustic environment?
Uh, so by acoustic environment, yes, it does influence. For example, if you're listening to some music in a big concert hall, where there is a reverberant environment, and immediately we can tell, right? We're listening to this in a big hall and there is a reverberant environment. So the signal gets modified in terms of some echoes come into the picture. Right? So that is the effect of acoustic environment. So it does not change the musical attributes, but it has a lot of effect. In the sense, it can give rise to a very rich effect, and people might like to listen to it like that.
But it will create any difference while you do modeling of that signal, or
Yes.
kind of machine learning applications?
Yeah, it will create this thing. For example, if you're going to take that kind of signal and try to find, let us say, the pitch versus time, it's going to be a bit challenging because it is actually a signal which has become a bit degraded by the reverberation. In the sense, a lot of echoes have come into the picture, right? So we'll have to have some special ways to process it. So that's another research problem, that if you get some kind of specific kind of degraded, what we are calling degraded, actually it's degraded from the point of view of the application. You're trying to extract the pitch. It actually may be a very nice signal in terms of listening, right?
Yeah.
But,
yes.
so you have to define your task, and then obviously you might have to change some of the signal processing depending on the nature of the signal you are receiving.
Is there any algorithm that deal with this kind of effects, like how to extract the feature that is independent of the acoustic environment?
Yeah, there is a lot of research in that. In fact, even other things, like you have a mix of many, because in the studio, they have these independent tracks and then they mix it all, and then what you get finally is a mixture of all the instruments. So another huge research area is called source separation. How do you separate the instruments in the mix?
Yes.
Okay. And similarly, they also add a lot of audio effects, correct? So when they produce this thing, they might take one of the source and they might add some reverb or echo to make it sound better, then mix it, correct? So one very big research area is about how to recover the original sources or the original audio tracks from this, mixture, which has also been, individual tracks have been modified. So
Okay.
that's, in the, like I told you, the music production application.
Yeah, yes. And how the language difference being captured while you go for processing the signal? Like if the same music versus same music, but in different language.
Okay.
Means the same lyrics, but in different languages.
Right. So language, actually the words will be different because they are from different languages. So if the tune is the same, then the fundamental frequency of the pitch versus time will be the same. Okay.
Yes.
But the lyrics will be different. So, that will, like I told you in speech, but when we change our resonances of the vocal tract, that is how we change the sounds we produce. So the overall spectral amplitudes are different when you are singing different lyrics, and whereas the pitch remains the same.
Okay. Thank you, ma'am.
Yeah, you're welcome.
Any more questions? Ma'am, what about this application of speech to the medical field, maybe for diagnosis or for healing? Anything would you like to highlight on this?
Yeah, in the medical field, especially if there are some, diseases of the speech production mechanism, such as the vocal cords, that can be made out by analyzing the abnormality of vocal cord vibration. Okay, so that can actually be found out. So there definitely are, pathological and clinical applications, many, or even in fact, in stroke patients, they're trying to find out the intelligibility of the speech in order to give them feedback on the speech therapy exercises, whether they still need to, do more speech therapy or what kind of therapy and so on. So there are multiple applications there, yes.
I think recently during this COVID days, ISC Bangalore, they have come up with a proposal to detect it from the speech. Do you think that is possible?
actually what they were trying to do is to detect it from the cough. They were saying that COVID cough is different from other coughs. Now
Okay,
see,
okay, that's how. Okay.
has come to such a point that we have a big database and you have all these COVID cough and non-COVID cough and so on. First of all, a human being should be able to tell the difference. Okay, chances are a bit bleak if even a human being can't tell the difference between the two coughs of a non-COVID and a COVID patient. Now, if a human being can do it, then you can, in principle, teach a machine to do it by collecting a very large label database, getting into that spectrogram type of representation, and teaching the machine the difference by just showing it many examples of both categories. Okay, so that is what they were trying to do, I think.
Yeah, some form of automation. First, if human can learn it, then some form of automation can be put into it.
Correct.
Yeah.
Yeah, so that is the state of the scene now. So people just try something blindly. They need to understand that it's possible, and have at least a feel for how it might work, and then only it's worth building that application.
Okay, okay. Any more questions from any of the participants? I think that's it. So
Okay.
thank you very much, ma'am, for accepting my invitation. And really, it was a very clean and clearly you have explained so many basic concepts. So thank you so much for your contribution.
Yeah, you're most welcome. And if you have any feedback, I'll be glad to receive it.
Sure, madam. Sure. Oh.
Okay, thank you all the audience who stayed through this on a Sunday afternoon.
Yeah, I know.
Yeah. Okay, Professor Patnaik. Yeah.
Thank you.
Bye.
Thank you, ma'am.
Yeah, all the participants. So day 4 is over. One more day. So tomorrow, I believe the morning session will be very interesting. That was by Professor. That will be by Professor Dipti Prasanna Mukherjee from ISI Calcutta. And thereafter, again, the 2 sessions, hypospectral image processing, and if possible, I'll be giving the last one, that is on LSTM. Okay, another model of deep neural network. And thereafter, we'll have the feedback session followed by the quiz test. So for the feedback session, I would request you all to turn on your camera so that I can capture the screenshots to have a proof that yes, these are the participants and they were present in the FTP. So that's it from my side. So see you again in tomorrow morning.
Ma'am, may I know the duration of the quiz, ma'am?
Sorry, could you please repeat?
How long the quiz, ma'am? 30 minutes?
No. Quiz will be after all these things gets over. Valedictory, that if you people want to give some feedback, so all these formalities are over, then I'll be sharing with you one Google form, and you can take 2-3 hours. That is very simple. We'll be having around 30 questions and mostly fundamental things. And today, if possible, I'll share all the PPTs with you.
Okay. No, quiz, we can attempt quiz up to 8 o'clock, no? Night, evening 8 o'clock.
Yeah, that's okay. But
Yeah,
by tomorrow night only, don't keep
yes,
it
ma'am,
pending for day
because
after
I go by
tomorrow.
transportation, my college transport.
Yeah, that is fine.
I leave at 4:30 campus.
Yeah, but
while
should be on
traveling, I
that.
can take quiz. That's fine.
Should be on tomorrow. It should not go for the
Yeah,
respond
yes.
on day after tomorrow.
Thank you. Right now. Okay.
Yeah, that's it.
Thank you.
Any more queries from anybody?
Thank you, ma'am.